going to do assignment 37, and we're going to start with FRQ 25. So we're going to look at the picture. So I'll just redraw the picture. So we have here 5.2 newtons, and then we have an outer cylinder with a force here that is 7.4 newtons. So it says the object above is a double tier pulley with a moment of inertia of 3.6. So I'm going to write that down, that I is 3.6 kilogram meter squared. The inner radius is 20 centimeters. So I'm going to call that R1. And when I physically write 20 centimeters, I know right away this is in meters, that I need to convert that to my standard unit, so it would be 0.2 meters. The outer radius is 40 centimeters, so R2 is 40, and again, I'm going to convert it in the beginning so I don't forget, and that's why we write down our given. A string over the pulley creates tensions as shown. Determine the net torque acting. So first of all, for part A, the net torque, I'm basically going to sum my torques, and the sum of my torques is equal to FR. So it's the force. Remember, my axis of rotation is here. So it's my force times the distance to this axis of rotation. Now, when we're doing torque, it's just like force. You have to establish your sign convention. So the standard sign convention is counterclockwise is positive. So just like I put my sign convention before my force, I'm going to put my sign convention before my summation sign. So it should look like this, that counterclockwise is positive. So now I'm going to add up my torque. So first I'm going to do this one, 7.4 times this distance to the axis of rotation. Now this one, look at the way it's going like this. So here's my axis of rotation. It's going this way. It's counterclockwise, so that's positive. So it's 7.4 newtons times 0.4 meters. This one is going this way. That one's going clockwise, so that one is negative 5.2 times 0.2 meters. So this is 2.96 newtons minus Newton meters minus 1.04 Newton meters. So my final torque is equal to 1.92 Newton times a meter. So that's part A. For part B, it says find the angular acceleration. So angular acceleration is alpha. So I know torque is also equal to I alpha. But remember, in a lot of these problems, whatever answer you use for part A, you're going to use for part B. So you see here, I already have the torque. Okay? They gave me the moment of inertia, so I'm going to use this answer here, and now I just need to find alpha. So I'll just rearrange that equation and say alpha is equal to the summation of torque, which I found in part A, over the moment of inertia. So that's equal to 1.92 divided by 3.6. So when I do that on my calculator, it comes out to be 0.53 radians per second squared. All right, so now let's move on and look at number 26, the next FRQ. So we're going to do 3726. Again, I think it helps to, oh, this one doesn't have a picture. All right, so let's just go ahead and read this step by step. So it says a 5 kilogram sphere. So first of all, I know it's a sphere. And why is that important? Because it's important to know what is the moment of inertia for the shape of something that I'm dealing with. So for a sphere, the moment of inertia is 2/5 mr squared. It has a radius of 15 centimeters. So right away, I'm going to take that 15 centimeters and I'm going to convert it to meters. It experiences a uniform angular acceleration when it completes 30 revolutions at a point on the surface. So here's my sphere cross section, and it's going to, when it completes 30 revolutions, so it's going around, so that's theta is 30 revolutions, has a tangential velocity, so the velocity is equal to 50 meters per second. Determine the force applied for the sphere. So I want to find the force. So first of all, as I'm writing down all my information, I see that this problem doesn't say it, but this starts from rest. Because the force is what causes it then to rotate. So that's not clear in the verbiage, but this starts from rest. Okay. All right, so where do we start? Well, first of all, do we want anything in revolutions? No. So what I'm going to do is I'm going to convert this, and I know that 2 pi radians is equal to 1 revolution. So when I do this, the revolution in the numerator cancels with the revolution in the denominator. So 30 times 2 pi is 60 pi radians. So that's theta. They also tell us that this velocity is 50. So since this is in radians, I know that v is equal to r omega. So omega is equal to v over r. So this is equal to 50 meters per second over 0.15. So I know that omega, and this is going to be omega f, because if it starts from rest, this is omega f, is 333.3 radians per second. All right. Now remember, I want to end up finding the force. And what's going to happen is I know that in the end, I know that force is equal to torque, and this is what I said before, torque is also equal to I alpha. So I set these two equal, and then I can find the force. That force is equal to I alpha over r. The problem is I don't know alpha, but this is where I'm going to use my rotational kinematics, because omega f is 0, omega f is here, and I have theta, therefore I can find alpha. So I'm going to say omega f squared is equal to omega naught squared plus 2 alpha theta. So I'll rearrange the equation to solve for the unknown in terms of the known. So I'll say omega f squared minus omega naught squared over 2 theta is equal to alpha. So 333.33 radians per second squared divided by 2 times 60 pi. Now here's the place you might make a mistake. Maybe up here you should have multiplied the pi. I don't use the pi button, I press 3.14, because if I use the pi button I'm going to go out like 8 decimal places. So when you do all this on the calculator, alpha comes out to be 294.82 radians per second squared. So once I get this for alpha, now I can go back here and I can go ahead and solve for the force. So force is equal to I, the moment of inertia. Well, this is a sphere. So for a sphere, it's going to be 2/5 mr squared times alpha over r. So before I start plugging in, I see that there's an r squared in the numerator and an r in the denominator. So let me go ahead and cancel those. So f is actually equal to 2/5 mr theta. Now I'll go ahead and substitute in my values. So 2/5, the mass is 5 kilograms. Oh, I didn't write that down. 5 kilograms times r, which is 0.15, times 295. So when I put all that on my calculator, F comes out to be 88.5 newtons. So again, this is very typical of the type of problems we see, at least probably half of a problem, where what you're doing is you're going to have to do a conversion. That's why it's very important to really understand these conversions and make sure that your units are consistent. You know, are you doing stuff in, radians per second squared? Because a lot of times they are going to give you different information. And then the key here is torque is equal to torque. So Fr is equal to I alpha. And then once we do that, we saw that, oh, we don't have the angular acceleration. So we need to go back and use our rotational kinematics to then find the angular acceleration.